Hello, everyone. Welcome to Feedstuffs 365. I'm Sarah Muirhead. Joining us today is Dr. Jerry Shurson, Professor of Animal Science at the University of Minnesota. Welcome, Dr. Shurson. Nice to have you with us again.
Well, thanks, Sarah. It's good to be back.
For those of you that are joining online, we invite you to post your questions there in the chat on your screen, or if you're joining us from social media, you can post your questions directly in your social feed. The prevention of African swine fever virus in North America continues to be a top priority for the U.S. pork industry. Feed ingredients can potentially be contaminated with this virus and serve as the route of transmission to pigs. So Dr. Shurson, I know you've been doing a lot of work in this area and you've got some new things to talk to us about. Let's start by having you tell us more about the contaminated feed and what role that can play in causing ASF infection in pigs.
Yeah, it's been quite a journey so far, and we've got a lot more to learn. But what we've learned so far is that if we experimentally inoculate feed ingredients with African swine fever virus, for example, it can survive for a fairly long period of time, especially in soybean meal. But what we don't know, and I keep emphasizing this to a lot of groups that I have the opportunity to share our work with, is that we don't know the prevalence of contamination or the concentration of the virus in real world conditions, especially in imported feed ingredients that we bring into the U.S., such as soybean meal and corn from countries that actually have African swine fever virus present, such as those in Asia and parts of Eastern Europe. And so if I could have the first slide, yeah. A lot of the reason for this is that we don't have a system in place. And I think this is really important. We don't have a system in place to accurately measure, monitor, prevent, and control African swine fever virus and other virus contamination in global supply chains. And if we account for the high amount of uncertainty that exists because of the lack of this surveillance or monitoring system, we actually conducted a quantitative risk assessment on the likelihood of importing African swine fever virus in contaminated soybean meal or corn from countries that we import from. And we did this study a couple years ago. And notice that we've accounted for the high uncertainty, which explains the wide range in estimates. In other words, a container of soybean meal coming from an ASF infected country has the likelihood of being contaminated once every 21 to 1,563 years, or for corn once every 66 to 5,000 years. So that wide range just illustrates, I think, the high amount of uncertainty that we have about the real world potential for this to occur. And the fairly large numbers, or the frequency of 21 to 66 years on the bottom end, indicate that the risk is low, but it's not zero. And so I think the important point here is that because there's not zero risk, we still have to do our due diligence and protect our feed supply chains, particularly in a global economy like we're in, to avoid the potential for contamination and getting it into the U.S. And so as a result, biosecurity protocols are essential to minimize virus contamination and the potential for spreading it coming into the U.S. and going to pig farms. In fact, it's so important that as of 2022, the FDA finally came out with guidance for the feed industry that does designate viruses as reasonably foreseeable hazards in feed ingredients. And this didn't exist before then. So the industry's made a lot of progress, and our government regulations now finally acknowledge viruses as a significant factor. But the missing pieces of all this, which really drives our research here at the University of Minnesota, is trying to understand how we put together these biosecurity protocols if it is contaminated in certain ingredients, and and what we can do in feed mills and pig farms to mitigate some of these strategies.
So feed protocols have been a relatively new addition to the overall prevention and biosecurity program for the pork industry, as well as one of the new practices, we've seen out there is to extend that storage time for potentially contaminated feed ingredients. And the premise there is to inactivate viruses to a level that makes that feed safe. Talk to us about that. What all this takes place here, and what is your thinking on this?
Well, you're exactly right, Sarah. And one of the strategies that has become pretty popular is the use of extended storage. And so, even though it's being implemented and seems like a reasonable strategy, one of the things that I really enjoy about working with our research team of Declan Schroeder and Pedro Uriola and others here at the university is that we're always not just answering the questions, but questioning the answers. We're always trying to reflect on what do we know? Is this reliable information or is it not? Which really led us to some of the research that I want to share with our audience here today. Work that was funded by the United Soybean Board, as a matter of fact. And the first step is to ask the question, is African swine fever virus inactivated during extended storage times under real world conditions? And one of the reasons that we're questioning previous work and previous recommendations is that the few studies that have been conducted in this area have used a variety of different assays and different tools to assess African swine fever virus inactivation during extended storage under different time and temperature conditions. And I like this slide because I think it's just a very nice visual summary to recognize that all of the different assays that have been used in experiments like this, or the different analytical methods, have limitations. Some are artificial methods, some are limited in sample size, some have too many variables to manage. Others are more indirect measures like the HAD assay and TCID 50 assay, which for some people in our audience, they may be familiar with some of those measures, which are really common, but they're indirect measures. They're not direct measures of virus. And then we have several others that have been used that lack context. And so because of different methodologies, different experimental conditions, different assays, we have this mixture of different results that are somewhat inconsistent and caused us to raise some questions about does this virus actually become inactivated under extended storage conditions? And so what we did is a couple of years ago, in what we call our foundational work, we published a study which we're all really proud of, and it shows that using a surrogate virus called Emiliania huxleyi virus, it's kind of a hard name for me to say, so I'm going to abbreviate it EHV, and African swine fever virus are very similar in their structure and in their functional characteristics, which makes EHV a really nice surrogate to study African swine fever virus in feed ingredients and digestive systems and all kinds of other applications that we haven't been able to do up to this point because of the high biosecurity requirements of working with ASF, because it's very transmissible and very contagious. And obviously we don't want it to get into the industry. And the other part of this study is we're using a different technique compared to the traditional real-time PCR or quantitative PCR that we're calling viability PCR, which actually helps us measure real viable virus particles if they exist in some of these materials. And so putting this surrogate virus assay together makes it safe because this virus only affects marine algae, the algae that grow in oceans. And so it's safe to use in pigs, in people, in plants, doesn't infect any of those. And because of its characteristics, it's very comparable to African swine fever virus. And just let me show you a couple of examples of why we're really happy with having discovered this important surrogate. Here's a side-by-side comparison of the African swine fever virus structure and the EHV virus structure. Notice that the envelope or the outer lipid membrane is very similar between the two. They both have capsids and they both have an inner membrane. Even more importantly, when we did a side-by-side comparison of EHV, which is in panel A, and African swine fever virus in panel B, and we exposed these viruses to increasing temperatures from 4 degrees Celsius up to 100 degrees Celsius, notice that the pattern of inactivation is very similar between the two. In fact, very little decrease in viable virus concentration occurred until we got to 100 degrees Celsius. And to do the conversion, that's essentially the boiling point for water, or 212 degrees Fahrenheit, for 20 minutes. And the pattern is the same for both viruses. And so there's still viable virus remaining, whether we're using the EHV surrogate or the actual African swine fever virus at 100 degrees by measuring the viability of the viruses. Now, the reason that this is important, and again, we verified this, and this diagram somehow got a little bit misconstrued here, but what it's intended to show is that we used another technique just to verify or to visualize that, yes, these little green particles that you might see, and this is, apologize here for this slide, but these little green particles are actual virus particles, and it indicates that they're still present after heating at the 100 degrees Celsius for 20 minutes. So this gave us a lot of confidence that using this surrogate EHV virus gives us very comparable results to what we'd expect with African swine fever virus. And the reason it's important is because two things. One, all the previous assumptions from previous studies would indicate that heating at 60 degrees Celsius for, let's say, 15 to maybe 30 minutes was believed to be sufficient for an activation of African swine fever virus. We now know, using the surrogate and showing you the side-by-side comparisons, that it takes more than 100 degrees Celsius for 20 minutes to partially, not completely, but partially inactivate this virus. And so the other part of this story is that for people that work in feed mills and the feed industry, I think we all recognize that reaching a temperature of 212 degrees Fahrenheit or 100 degrees Celsius in real world feed ingredient storage conditions doesn't happen. And so the extended storage story was a bit suspect, and that's why we did this study. And so just to give you a brief overview of what we found in this extended storage stability study, we evaluated several different ingredients: complete feed, corn fermented protein, DDGS, high protein DDG, extruded soybean meal, solvent extracted soybean meal, and soybean hulls. And regardless of the corn or soybean based ingredient, there was very little inactivation, as we expected, storing these inoculated ingredients with EHV anywhere from 4 degrees to 24 to 34 degrees Celsius, which is about 95 degrees Fahrenheit was the maximum temperature we used. And we took these out to 120 days of storage. You'll see that there's some pretty big boxes here. These are box plots showing how much variability in estimates or what the range was in some of our estimates. And that's partly because of the experimental error of the assays that we were using. But essentially, there was very little, less than 1 log reduction in concentration at this temperature of 94 degrees Fahrenheit at 120 days. And so we're pretty confident that these results really require us to rethink whether this extended storage protocol for biosecurity is really valid for African swine fever virus.
Very interesting. And we do have Dr. Shurson here with us live. So if you have any questions, please post those there in the chat, either in your social media feed or on your screen, and we will make sure that we address those. We've also posted links to 2 articles on this topic that Dr. Shurson has authored in our January digital edition of Feedstuffs. So let's continue our conversation. You're talking about these new results that indicate ASF viruses is more heat resistant than previously assumed, and as a result that we need to perhaps reevaluate biosecurity protocols involving time and temperature treatments related to the ASF virus, and especially looking at that practice of extended storage. So what have you learned about feeding ASF virus contaminated feed to pigs and the likelihood of it causing disease?
So that's another big unknown that we're trying to understand. And you're right, sir. I mean, ultimately, none of this stuff matters. What matters is if I have contaminated feed, is it going to make my pigs sick? And that's what we're trying to understand of getting into the mechanisms of what are the conditions, if they exist, that feeding contaminated feed ingredients would cause pigs to develop an infection for ASF. And so I think, again, I like to go back to the fundamentals on all these things and see the big picture and just remind everybody that there are a lot of steps that have to happen from the time that an ingredient would be contaminated with a pathogen like African swine fever virus until it ends up in the feeder on a farm and causes a pig to get sick. You know, first of all, the pathogen has to be present in the ingredient at some measurable concentration, probably above what the minimum infectious dose might be to cause an infection in pigs. And then it's got to survive the time and temperature of drying, processing, and storage. And so the previous results I just shared with you would indicate that for African swine fever virus, if it's present in these different corn and soybean-based ingredients, storing it at 95 degrees Fahrenheit for 120 days isn't going to degrade it very much. So it would still be a pretty high risk proposition. But then it also has to go through a transport from wherever it might be imported to the feed mill and then stored at the feed mill until it's blended with other ingredients to make complete feed. And the concentration needs to be greater than whatever that minimum infectious dose might be for the virus, and it must be in a viable form capable of causing an infection if it's consumed. And so what was interesting is that when we read some of the earlier studies, and there really have been 2 studies conducted to help us understand what amount of virus for African swine fever is needed to cause an infection in pigs. One study was published by Megan Niederwerder, who now is the director at Swine Health Information Center. And her work showed that 10,000 virus particles in one exposure was enough to cause an infection in pigs. And so that's what we would call the minimum infectious dose of ASF in feed. In contrast, a group of Spanish researchers that have been working a lot in this space for several years, Blasquez and others, published a different study where they fed liquid plasma containing 100,000 ASF virus particles, or 10 to the 5th TCID50 as our measure, And they fed it continuously for 14 days, and the pigs didn't get sick. So here's a higher concentration or a higher dosage, continuous feeding, no infection, versus a lower dose, one exposure causing infection. Caused us to ask the question, how can this be? How can you come up with two very different answers? Well, I think, part of this was really unexpected with the BLASCAS results of feeding the liquid plasma contaminated with virus for 14 days, because we've learned from some of Dr. Niederwerder's work that frequency or the number of exposures, the number of meals that a pig would eat naturally throughout the day, as that increases, the likelihood of infection increases even at lower doses. But what we wanted to really understand is, once a pig consumes these types of ingredients or complete feed, what happens to the fate of African swine fever virus using this EHV surrogate, which is the only way we could actually do this laboratory-based study in the first place. What would happen in a simulated stomach, small intestine, large intestine digestion environment to these viruses if it's inoculated in some of these different ingredients? And so we use this laboratory-based simulation of a pig gastrointestinal tract to study the extent of EHV degradation in these three different sections when samples of corn co-products, and soybean meal and hulls were inoculated. And what our results showed in the stomach and small intestine portion was that there are two main points here. First, notice here at the bottom, I've got the designation of the different ingredients that we evaluated. Notice that the soy-based ingredients are here on the far right-hand side, and the amount of degradation that occurred in the upper part of the GI tract was less. In other words, soybean products tend to be more protective as we continue to learn of this virus than other types of ingredients. And so there was less degradation in the soy-based products compared to the corn-based products, which are shown here on the left-hand side of this plot. So there were differences between the broad categories of matrices, which tells us that the chemical composition of ingredients or diets probably makes a difference. However, there wasn't a huge reduction, on average about 2.8 log reduction, regardless of ingredient, across all ingredients that occurred during this digestion stage. And then when we extended this to the large intestine portion of the digestion process or the fermentation process, here's where we saw even greater degradation for almost all of these different ingredients, with the exception of solvent extracted soybean meal. And yes, that was degraded too, to a large extent. On average, all of our ingredients were reduced by about 3.8 logs on top of the 2.8 log average from the small intestine and stomach portion, giving an overall reduction of 5 to as much as 7 log reduction across the entire GI tract. So what these results tell us is that diet composition, or the types of ingredient chemical composition, probably makes a difference. And there is significant degradation of this virus that occurs in the digestive process of pigs. And these results might partially explain why feeding different types of African swine fever virus contaminated diets result in different types of infectious responses. So we still have a lot more to learn, but I thought our audience today would be interested to see maybe what happens in the GI tract of pigs using our in vitro digestibility assays that we've used for a number of other types of nutritional studies.
Great information. So Jerry, a question for you in terms of, as a feed manufacturer, should you be still doing that extended storage? What's your recommendation? Still too much to learn before we make some of those recommendations, or, where should we be on that?
Well, I think the data that I presented here today, and what we know about the thermal resilience of African swine fever virus, I would say that we ought to be looking for other strategies. Obviously, prevention is the best solution. I think we need to be a lot more progressive in developing biosecurity protocols farther up the chain at the farm level for imported ingredients, or even the processing level, and do some auditing to try to minimize the potential of contamination prior to importing these from ASF infected countries. I think extended storage, on the other hand, can work really well for a lot of our RNA viruses like PED virus, perhaps Seneca Valley, and some others that aren't quite as temperature resistant as ASF. But I think if our goal is to target ASF as part of that protocol, extended storage is not a reliable strategy based on our data, and probably there's some evidence from a few other studies as well.
Very interesting. So what would be your key takeaways then that you want to leave our audience with here today as we wrap up?
Well, I think the key takeaways, and this is part of, I think everybody's been really pleased with the progress made by the U.S. SHIP program, the Swine Health Improvement Program, which does include feed as part of the biosecurity plan. And so I think the takeaways are, we need to move our biosecurity protocols closer to what are being used in the food industry, and think about farther up the chain. I think doing our due diligence and asking questions about where our feed ingredients are coming from. Is there a risk for virus contamination, especially ASF? And if so, there are some chemical mitigants out there that I think have clearly shown some real benefit, and those probably are more useful tools than extended storage for ASF that should be considered if people are suspect of contamination of imported ingredients. As far as routine use here in the U.S., we don't have this virus, or at least not that we know of, and I hope we don't. Mm-hmm. And so keeping it out of the country is the main goal. And certainly, some of these kind of strategies for domestically produced soybean meal, corn, other byproducts probably doesn't matter at this point, because we don't have to worry about transmission within the U.S. But certainly other types of viruses can be found in some of these ingredients that we ought to be aware of as well. So chemical mitigants, I think, are probably our best strategy beyond prevention and biosecurity protocols. So I'd encourage everyone to maybe take another look at, what does your feed supply chain biosecurity look like? And are there some gaps that could be shored up to tighten up some of the preventative aspects that might be needed?
And it's always good to be prepared, just by chance, if we happen to get the virus here in the United States. Let's understand it and know about it so we can minimize its impact. Absolutely.
And lastly, I do want to acknowledge again, United Soybean Board has been a really, really important and great supporter of this work. And again, I think we've learned through not only our work, but work of others, that for some reason, soybean meal seems to be somewhat protective of this virus. We don't know why. We're still trying to conduct some experiments to figure that out, but it does seem to be more susceptible compared to, at least in our work, some corn-based ingredients and perhaps others. So there are differences among ingredients, it seems.
That's interesting. So, Dr. Jerry Shurson of the University of Minnesota, thank you so much, Dr. Shurson, for joining us here today. We always appreciate your insight.
Thank you very much, Sarah.
And don't forget to check out those articles that are posted there in the chat. There's great information to more extensively look at these topics. Likewise, we appreciate all of you tuning in. A reminder that all Feedstuffs 365 segments are available on demand on feedstuffs.com. Until next time, for Feedstuffs, I'm Sarah Muirhead.